Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on liquid extraction. This will be part number 4 of my discussion on liquid extraction, and today I'll be talking about liquid-liquid equilibria. Why liquid-liquid equilibria? Because liquid extraction involves contact of two insoluble liquid phases, and how equilibrium is reached between these two insoluble liquid phases, that is what we need to understand. Understanding of the equilibrium between the two insoluble liquid phases is important in liquid extraction. So that's why today we will be understanding liquid-liquid equilibrium. Under this, I'll be discussing two different ways of representing liquid-liquid equilibrium. One is the binodal solubility curve. So we will understand that in details. And the other one is the distribution diagram. We will understand this also in details. So today you are going to know what is a binodal solubility curve, and then you are also going to know what is a distribution diagram. So let us first understand what is liquid-liquid equilibrium. So for that, we will consider a simple example where there are three liquids, liquid A, B and C. And we are going to see what happens when these three liquids are mixed together. Now, among these three, A and B are completely immiscible in each other. They are completely insoluble in each other. Whereas C is miscible in both A and B. C is soluble in both A and B. Now let us understand, if these three liquids are mixed together, then how equilibrium is reached in this system. So let us say that we are mixing liquid A, liquid B, liquid C, and then the resulting mixture is properly agitated, and then it is allowed to settle. So after some time, the mixture will separate into two layers. Why? Because A and B are completely immiscible in each other. So one would be the liquid A, one layer will be of liquid A and the other will be of liquid B. Whereas solute C will be present in liquid A and it will also be present in liquid B. And as the mixture is separated into two liquid phases and C goes in each liquid phase, but what is actually happening, C is moving from liquid A to liquid B, and at the same time it is moving from liquid B to liquid A. But after sufficiently long time, what happens? The rates of these two processes, which two processes? The process of C transferring from liquid A to liquid B and the process of C transferring from liquid B to liquid A. So after sufficiently long time, the rates of these two processes becomes equal. That is, the amount of C moving from liquid B to liquid A is same as that is moving from liquid A to liquid B. So amount of C moving from A to B is equal to amount of C moving from B to A. So if I say that R1 is the rate of transfer of C from A to B, and R2 is the rate of transfer of C from B to A. Then what is happening? After sufficiently long time, these two rates become equal. That is, the rate at which C moves from A to B becomes equal to the rate at which it moves from B to A. So when such a situation is reached, we say that the two liquid phases are in equilibrium. The two phases are in equilibrium. So if the two rates are same, then there is no net transfer of no net transfer of C across the interface between the two liquid phases. Across the interface, there is no net transfer. That is, concentration of C, it remains constant at a particular value in liquid A, and it will be constant at a different value in liquid B. So this is a case of dynamic equilibrium. Although C is moving from one phase to the other phase, there is no net transfer of C. So in this way, equilibrium is reached between the two liquid phases. Here we have considered that A and B, they are completely immiscible in each other. That's why no B goes into phase A or liquid A, and no A comes into liquid B. I hope you have understood the concept, how equilibrium is reached between two insoluble liquid phases after a sufficiently long time, and why we are calling it as a dynamic equilibrium. Now let us consider the common case in liquid extraction. Commonly in liquid extraction, A and B, they are soluble in each other to a limited extent. In my earlier discussion, I had considered that A and B, they are completely immiscible in each other. Now, I'm talking about the common situation that occurs in liquid extraction. What is that situation? A and B, they are soluble in each other to a limited extent, whereas C is soluble in both A and B. So now let us see how equilibrium is reached in this particular case. And if you want to know example of such liquids, you have water, chloroform and acetone. Water, that is A, chloroform B, and acetone C. So in this case, water and chloroform, they are soluble in each other to a limited extent, whereas acetone is soluble in water as well as it is soluble in chloroform. So if these three liquids, they are mixed and properly agitated, and then if they are allowed to settle, again they will settle in two layers, two liquid layers that are insoluble in each other. So again C will be present in both the layers, and it will be after a sufficiently long time, a dynamic equilibrium will be reached, where although C will be moving from one phase to the other phase, there will be no net transfer of C across the interface. So in this particular case, since A and B, they are soluble in each other to a limited extent, this phase will be containing, liquid A will also contain little amount of B in it, and liquid B, in that case, the phase will be A-rich phase. We will have to call it as A-rich phase because the major component in that layer is A. Whereas here in liquid B, there will be little amount of A that will be going into that layer, and that's why now it will be called as B-rich phase. So in the case of three liquids A, B and C, where A and B are soluble in each other to a limited extent, at equilibrium you have separation of A-rich phase and B-rich phase. The mixture separates into A-rich phase, which contains majorly A, then C and little amount of B, and B-rich phase, which contains majorly B, C and little amount of A. So at equilibrium, in this case, we will be having A reach phase and D reach phase. So this is how equilibrium is reached in this particular case. Now let us know about the binodal solubility curve. Let us understand what is binodal solubility curve. So again, we will consider the common case. What is that? A and B are soluble in each other to a limited extent, and C is soluble in both A and B. Now we are going to represent this liquid-liquid equilibria on the equilateral triangular coordinates. I have discussed about equilateral triangular coordinates in my previous video. I am giving link to that video. If you have not watched it, please watch it. So this equilateral triangle will be representing the liquid-liquid equilibria involving three liquids. Pure components will be represented by each apex of the triangle. So this apex is representing pure A, this apex is representing pure B, and this apex is representing pure C. Now, if you carry out a task, what is that task? B is added to A. You go on adding B to A. So you are carrying out a task where you have taken A in a beaker. This is A, and now you are adding B to this A. So if B is added to A, ultimately what will happen as you go on adding B to A? Ultimately, a stage will be reached where A reached saturated solution is formed. Why saturated solution? Because if you try to add any further B, any further addition of B will result in separation of solution into two layers. So we are going to add B to A so as to have A reach saturated solution. Why A reach saturated solution? Out of B, A and B, here A is the major component. Similarly, the saturated solution that is obtained, A reach saturated solution, you can represent on this equilateral triangular coordinates. In this case, it will be represented by point L. Now, point L is close to apex A, which indicates that at this point, the major component is A. That's why they are calling it as A reach phase. Similarly, if you carry out another task, if now A added to B, so now this time in beaker you are taking B, and from outside you are going to add A. So as you go on adding A to B, ultimately what will happen? You'll reach a stage where B reach saturated solution is formed. Saturated solution, that means if you try to add any additional A to the mixture, it will result in separation of the mixture into two liquid layers. Any further addition of A will result in separation of the solution into two layers. So this saturated solution, the B reach saturated solution, it is represented by a point, and I am calling that point as point K. And point K is located close to B, which indicates that at this point the major component is B. So at point K is representing B reach saturated solution of A and B. L is representing A reach saturated solution of A and B. Both L and K, they are representing a binary mixture, only two components A and B. So as A and B they could become more insoluble, what will happen? This point L will move towards apex A and point K will move towards apex B. So as the insolubility of A and B increases, the position of points L and K will be close to apex A. For point A, for point L, it will be located close to point A, and point K will be located close to point B. As the solubility decreases, L is going to move towards A and K is going to move towards B. The other way is also true. That means if solubility increases, then L is going to move away from A and K is going to move away from B. So, if the point to remember is position of L and K, it depends on mutual solubility of A and B. More insoluble they are, these points will be located close to those apices, apex A and apex B. More soluble they are, these points will be located away from A and B. Point L will be located away from A and point K will be located away from B. Okay, now let us consider a point J. Now, where is this point J located? Point J is located between L and K on the side AB. So, that means point J also represents a binary mixture of A and B. But let us understand it. Point J between points L and K, it represents a binary mixture of A and B, and in this case, the mixture will be containing two insoluble liquid phases. So, point J, it represents a two-phase mixture of A and B, two-phase binary mixture. One is, out of the two phases, one phase is A reach phase and the other phase is B reach phase. So, at point J, if I try to represent it, there will be a two-phase mixture. So, one is A reach phase and the other one is B reach phase. So, any point between L and K, it will be representing a three-phase mixture like this. One phase will be reach in A and the other phase will be reach in B. I hope you are understanding the concept. Now, the composition in A reach phase, when you have A reach phase and B reach phase, then composition in A reach phase, it will be given by point L, and composition in the B reach phase, it will be given by point K. So, point J, as I said, it will be representing a two-phase mixture, A reach phase, B reach phase. Composition in A reach phase, it will be given by point L, whereas composition in B reach phase, it will be given by point K. So, there may be many other such other points like J that will be lying between L and K. Each of them will be representing a binary mixture. Each of them will be representing a binary mixture where there are two insoluble phases. I hope this is clear to you. If you have any doubts, you please mention that in the comment section. So, now we have understood what is point J and what does it represent. Okay, now let us consider a task where we are adding C to the A reach phase. If C is added to the A reach phase, what will happen? Its solubility changes along a curve. So, as you go on adding C to the A reach phase, the solubility is going to change along a curve. And I am showing this curve with a green color. That's why I am calling it as green curve. And we call that curve as A reach solubility curve. So, you will be getting a curve. So, this curve is obtained by adding C to A reach phase, and this curve is called A reach solubility curve. On the other hand, if C is added to B reach phase, what is going to happen? Again, the solubility is going to change along the curve, and I am representing it by brown color. So the down curve that I am going to show will be the curve that will be obtained if you add C to the B rich phase, and that curve is called B rich solubility curve. So B rich solubility curve will be obtained. The two curves, that is the green curve and brown curve. You please remember the color that I am talking about. I have used those colors for my convenience. It has nothing to do with solubility or any other thing. In just to show, you have two different curves, or two different curves are obtained if C is added to the A rich phase and if C is added to the B rich phase. The two curves that you get, these two curves, they come together and you get the binodal solubility curve. So binodal solubility curve is combination of the two curves, combination of A rich solubility curve and B rich solubility curve. So this entire curve is said to be the binodal solubility curve, or it is called the binodal solubility curve. It has two parts. One is the solubility curve, A rich solubility curve, and the other one is B rich solubility. So now I'm sure you know what is the binodal solubility curve. Now, if you consider any point outside the binodal solubility curve, let us say point S. So if you are having a point that is lying outside the binodal solubility curve, such a point, any point outside the binodal solubility curve, it will represent a ternary mixture. Ternary mixture, that is mixture of three components. Which are these three components? A, B and C. Point outside the curve will represent a ternary mixture of A, B and C, and the ternary mixture, it will be a homogeneous liquid solution of single liquid phase. There will be only one liquid phase. Points like S that lies outside the binodal solubility curve, those points will be representing a ternary mixture of three components. Which are these three components? A, B and C. And this ternary mixture will be a homogeneous liquid solution of single liquid phase. There is only one liquid phase. Then if you consider any point underneath the binodal solubility curve, like point M. So now I am showing point M, and now point M is underneath the binodal solubility curve. So any such point, it represents a ternary mixture of the three components, that is A, B and C, but this mixture is separated into two insoluble saturated liquid phases that are in equilibrium with each other. Now we just now understood how equilibrium is reached between two insoluble liquid phases. So point M will be representing a ternary mixture, but the mixture is separated into two insoluble saturated liquid phases, and these liquid phases, they are in equilibrium with each other. That is, every point beneath the binodal solubility curve will be representing a two-phase ternary mixture. The two phases, they will be in equilibrium with each other. Out of the two phases, one phase is the A rich phase, and we call that the raffinate phase. So one phase at point M will be the A rich phase. It is called the raffinate phase, whereas the other phase is B rich phase, because in that B will be the major component, and that phase is called the extract phase. So every point beneath the solubility curve, binodal solubility curve, it will be representing a two-phase mixture where the two phases, raffinate and extract phases, they are in equilibrium with each other. I hope you have understood the significance of points like M, which lies beneath the binodal solubility curve. Now the equilibrium composition of A reach phase. A reach phase, that is represented by point M. Now we are talking about equilibrium composition of the A reach phase. It is given by the point R on the binodal solubility curve. So composition of A reach phase at point M is given by point R that lies on the A reach solubility curve. Whereas the equilibrium composition of the other phase, which is the other phase, the B reach phase, it is given by the point E, and this point E, it lies on the B reach solubility curve. So point E will be lying on this curve. So point R is representing composition of A reach phase at point M, and point E is representing composition of B reach phase at point M. A line that joins point R and E and it passes through M, that line is called a tie line. So we are talking about a line that joins R and E, which are representing the T equilibrium compositions, and that line passes through M, and that line we call that line as the tie line. A line that connects 2 points representing equilibrium compositions, that line is called a tie line. So point M lies on the tie line. Point M represents two phase mixture. One is A reach phase, the other one is B reach phase. Composition in the A reach phase is given by point R, and composition in the B reach phase is given by point E. The line that connects equilibrium compositions, we call that line the tie line. So having understood what is a tie line, let us also remember that there is an infinite number of tie lines on this binodal solubility curve. An infinite number. Like the tie line that we have shown over here. Tie line RE. Tuck means polling points you can note for tie lines. So these tie lines, end points of these tie lines represent compositions that are in equilibrium way. So in this case, for the tie line RE, end points are R and E, and R and E are representing compositions that are in equilibrium with each other. So that's why I'm saying tie lines, end points of the tie line represent compositions that are in equilibrium with each other. These tie lines, they are rarely parallel. That is, mostly they will not be parallel with each other. Their slope change slowly in one direction. Slope of this tie line, it changes. This tie line changes. That happens slowly in one direction only. So for example, I have shown this tie lines, and now you can see the slope of the tie line is changing in one direction only. So that is very common. But there are some cases for relatively few systems, the slopes change in both directions. That means some tie lines will be having slope in one direction, whereas the remaining tie lines may be having slope in the other direction. So in that case, for this case, there will be one horizontal tie line. And what is the significance of this horizontal tie line? This tie line separates tie lines with slope in one direction and tie lines with slope in the other direction. That means on one side of the horizontal tie line, we will be having tie lines with slope in one direction, whereas on the other side, we will be having tie lines with slope in the opposite direction. So the horizontal line, you can say, separates tie lines of slopes in different directions. So that happens for relatively few systems. Such systems are called solotopic systems, where slope of the tie line changes in direction. The direction of the slope changes. Direction of slope of those tie lines changes. And there is one horizontal tie line that separates tie lines of slopes in different directions. So I hope the concept is clear to you. If you have any doubt, please let me know. Now the A-reach solubility curve, that is the green curve in this diagram. Every point on that curve, it represents equilibrium composition of C in the raffinate phase. That means every point on the A-reach solubility curve will be representing equilibrium concentration, or you can say equilibrium composition of C in the raffinate phase. Whereas B-reach solubility curve, every point on the B-reach solubility curve, that is I am talking about the brown curve, every point will be representing equilibrium composition of C in the extract phase. Every point on the A-reach solubility curve will represent composition in the raffinate phase, whereas every point on the B-reach solubility curve, it will be representing composition in the extract phase, equilibrium compositions in the extract phase. The point at which A-reach and B-reach solubility curves meet, so the point where green curve, the A-reach solubility curve, is meeting the B-reach solubility curve, that is this point. This point is called, I am showing that point, I am calling that as point P, and this point is called the plate point. And what is the significance of this plate point? The last plate point is the last tie line. And since it is a point, length of that tie line is 0. Usually, the plate point will not occur at maximum concentration of C on the binodal solubility curve. That is, it will not be located at a maximum point on the binodal solubility curve. Usually, that will not happen. Usually, that's why I'm saying, usually the plate point is not at the maximum concentration of C on the binodal solubility curve. If at equilibrium, the concentrations of C in the B-reach phase, that is extract phase, is greater than in the A-reach phase, that is raffinate phase. So at equilibrium, if concentration of C in the extract phase is greater than corresponding concentration in raffinate phase, then we say that C is favoring B, that is C is dissolving more in B. So we say that C favors B. Whereas on the other hand, if concentration of C in the A-reach phase, that is raffinate phase, is greater than in the B-reach phase, that is the extract phase, then we say that C favors E. So both can happen. C may favor B. In that case, concentration in the extract phase will be higher, and C may favor E in some cases. In that case, the concentration in the raffinate phase will be higher than that in the extract phase. For successful extraction, of course, C should favor B. That is, the first case should be prevailing. C should be going into B. That is, concentration of C in the extract phase should be more than the concentration in the raffinate phase for successful extraction. So that's why I'm saying for successful extraction, C should favor B. So that was all about the binodal solubility curve. Now let us talk about the distribution diagram. The tie line data on the ternary diagram, the tie line data on the equilateral triangular coordinates, they can be presented in a different way. The tie line data on the ternary diagram, it can be presented in a different way on the distribution diagram. In this case, the concentrations of C, which are represented by aim points of a tie line on the ternary diagram, if these concentrations are plotted against each other, we get the distribution diagram. So that's why the concentration of C, which are represented by endpoints of a tie line on the ternary diagram, if they are plotted against each other, we get the distribution diagram. The concentrations are expressed as weight fractions, for example. Weight fractions. So weight fraction of C in the raffinate phase will be X. We are going to denote that by X. And the weight fraction of C in the extract phase, we are going to denote that by Y. And of course, this X and Y, they are in equilibrium with each other. Now, to obtain the distribution diagram, what is done? X, that is concentration in the raffinate phase, weight fraction in the raffinate phase, it is plotted on the x-axis, whereas Y, that is weight fraction in the extract phase, it is plotted on the y-axis. The curve obtained by plotting these two quantities, we call that curve the distribution curve, and the diagram is called the distribution diagram. So X and Y, this X and Y, they are in equilibrium with each other. So when you plot X against Y, you get the distribution curve, and the resulting diagram is called the distribution diagram. Okay, now let us understand how we get the distribution diagram and the distribution curve from the tie line data. So for that, I am showing the binodal solubility curve that I discussed. And now let us draw the distribution diagram. So on x-axis, we are going to plot X, which is weight fraction in the raffinate phase. On the y-axis, we are going to plot Y, which is weight fraction in the extract phase. And then for reference, I am going to draw a diagonal line. This is the diagonal line. Then the first thing is, I will get point P, which is on the binodal solubility curve on this diagram. So I will simply draw a line from point B so that I end up on the diagonal line of the distribution diagram. So point P will be represented over here. Then let us consider this tie line. And what I will do, let the concentration represented by this tie line in the raffinate phase, let it be Y1, X1, and in the extract phase, let it be Y1. So I'm going to get this X1 on the distribution diagram. So for that, I'll draw a horizontal line till I go to the diagonal line. And if I draw a vertical line from this point, I will get X1 over here. So now the X1, which is on the binodal solubility curve in this diagram, now I have got it on the distribution diagram. Next, I will get Y1. So for that, I will draw a horizontal line till I meet the vertical line that I have drawn through X1. And in that process, I am going to get this point. So this will be Y1. This is Y1. So this point, the coordinates of these points are X1 and Y1. Similarly, for the second tie line, let the endpoints of this tie line represents compositions X2, Y2. I am going to get X2 first on the distribution diagram. So I'll draw a horizontal line, come to the diagonal line, and then I'll draw a vertical line, and I'm going to get X2 over here. Now let us get Y2. So for that, I will draw a horizontal line from this point till I reach this point, and I get a point whose coordinate y coordinate is y2, x coordinate is x2. Now for the third tie line, let this composition be x3 and this be y3. So first I will get x3. So for that I will draw this horizontal line, go to the diagonal line, and then if I draw a vertical line, I am going to get x3 on the distribution diagram. And for getting y3, I will be drawing this horizontal line. I will get y3 over here. So in that process, I get this point. And finally, for the last tie line that I have shown over here, I'm going to call this as x4, and then this x4 will be obtained on the distribution diagram in this way. So this will be x4, and this y4, it will be obtained over here. This is y4. So y4 is obtained over here. So in this way, I get 4 points. Now if I draw a curve through these 4 points, the curve that I will be obtaining will be the distribution curve, and then this diagram will be the distribution diagram, because this curve is telling you how C is distributed between extract phase and raffinate phase. So the curve that is obtained in this way is the distribution curve. So this is the distribution curve, and then the diagram is then the distribution diagram. So in this way, we have represented the endpoints of each tie lines on the distribution diagram. Endpoints of each tie line represents compositions that are in equilibrium with each other. So on the distribution diagram, we have actually plotted equilibrium concentrations. So that's why this curve, you can also call it as equilibrium curve. So I hope now you know what is the distribution diagram and how you can get it from the Binodal solubility curve. So this is the distribution diagram that we obtained, and now you can see over here the distribution diagram is lying above the diagonal line. What is the suggestion? The suggestion is that what is the meaning of that? At every point on this curve, y is greater than x. That is, concentration in the extract phase is greater than in the raffinate phase. In other words, in this case, C favors B. So I have shown a distribution diagram which for the case where C is favoring B. For the other case, that is when C favors A, the distribution curve will be lying below the diagonal line. For example, it may be like this. For this curve, if you have various points, then this curve will be for the case where C favors E. C favors E. If the curve is lying above the diagonal line, C favors B, and that is very much required for successful extraction. So with this, I end my discussion on liquid-liquid equilibria. In today's discussion, I have described what is the binodal solubility curve and then what is the distribution diagram. Both of them are different ways of representing liquid-liquid equilibria. So with this, I end my discussion for today's topic. I hope you have understood the concepts. If you have any doubts, you please mention them in the comment section. Thanks for watching my video. Thanks for being with me. Do subscribe to my channel. Tell your friends to subscribe to it. If you have any doubts, you please mention them in the comment section. You please hit the bell icon so that you'll be notified as soon as I upload any new video. For now, have a nice day. Bye bye.